All right, so here when you walked in, you picked up a salmon formula sheet. This is a replica of the same formula sheet you're going to get when you test from me. So you'll get a new copy of this when you're actually testing. Someone asked today if they could, we're going to discover a couple extra formulas and hints when we get to the angular velocity and linear velocity section. And they said, can I add those to my formula sheet? And I said, for the art of practicing your homework, yes, but you're not going to have access to anything additional than what's on here for your actual test. So don't start relying on formulas that aren't on here if that's the way you're practicing. All right, so on the back of worksheet 2, this little area here, this is talking about how you find angles within the trig proportions, and we discussed this yesterday, how you're going to use inverse cosine or inverse tangent or inverse sine to undo the sine, cosine, and tangent function. So we already talked about that. We're going to skip that, but we're going to discuss first the applications of the trig proportions. And for PreCalc, because this is not your first rodeo, guys, you've done these for quite a few years now, you're going to often find that these questions don't have any diagrams drawn for you, especially the more basic ones, like the ladder leaning up against the house kind of questions. So a concept that we run into problems with sometimes at all levels of math are where the angles go. So they're going to say things like angle of depression and angle of elevation, and you have to kind of remember what that means. So angle of elevation would be an object or somebody at a lower level, so this is you down here, and you're looking up at an object. So the angle of elevation is the angle between your target and then the ground. They always call it the ground, but it's not really the ground, it's whatever your horizon is. It doesn't have to be on the ground even. So that's angle of elevation, but let's talk about this for a minute. What if I'm up here? Or at least my eyes are. So when I'm at the top of the triangle, I'm looking out at what's called an angle of depression. So where's my angle of depression? It's over here. What's the problem with that green angle that I just kind of highlighted there? It is the same as the red angle, but the green angle is not actually in my triangle, right? So we run into issues, thank you, with students who are just reading a problem and it says something like the angle of depression is 30 degrees. Well, this angle right here is 30 degrees, but that is not this angle in the triangle. So sometimes kids will put the 30 in the wrong spot. So what you end up doing is in your brain, you need to run a little synonymous moment here. So angle of depression and angle of elevation are congruent angles. Someone want to really impress me with their geo knowledge? Why are they congruent? Very nice. Alternate interior angles are congruent. So angle of depression and angle of elevation are always the same thing. So whenever my problem starts spouting out something about angle of depression or angle of elevation, I just know that it's going to be the angle that's down in the bottom corner of your triangle. Now, if you draw stellar diagrams like I do, pretty much all your triangles look the same. You just draw like a really dorky triangle, even though it doesn't fit the picture, and that bottom corner is always your angle. Just be careful where you're putting your angles. The other problem we run into, and I hope we don't run into it too much in PreCalc, where are shadows located? On the ground. Yeah, on the ground. Where do those little kids put the shadows in these problems? On the hypotenuse. Which is weird. Yeah. Shadows aren't flying through the air, guys. They're on the ground on these questions. You're like, really? People do that? Yeah. You used to do it, believe it or not. In Algebra 2 and before that, possibly. All right, so they kind of go through a bunch of these examples of angle of depression and elevation. Let's see some examples here. You're about to be treated to a very beautiful picture drawn by me. It's the Leaning Tower of Pisa. You think I'd get smart and get a diagram going before I get here. All right, so the Leaning Tower of Pisa, like this, yes? It leans, and it's 55.9 meters. So the length of the tower is 55.9. Normally towers are perpendicular to the ground, but not this one. And it is leaning so that if you were to measure the top down straight to the ground, whoop, that is a measurement of 55 meters. So we know any measurement that goes from top straight down to the ground to horizontal, that would be the vertical leg of your right triangle. And they want to know what is the angle at which the tower is leaning. So that's kind of a vague question. I kind of wish they would have worded it a little differently. They're looking for this angle down here. So I need to decide which trig function I should be utilizing. Clearly this is the hypotenuse. And then if this is the angle we're interested in, this is the opposite leg. So which trig function utilizes opposite and hypotenuse? The sine ratio. So you have the sine of mystery angle equals opposite over hypotenuse. Now, if you're using one of my yellow calculators, you might need to change the mode back to degree quite often because my Algebra 2 students have to reset their calculators a lot, and it defaults back to radian mode, so be careful about that. Someone remind me, how are you going to undo a sine function? You're going to use inverse sine. Very good. So what you're technically doing is you're applying the inverse sine to both sides of your equation. You guys know you're just typing inverse sine of the ratio. And let's see, 79.7 degrees, maybe? Okay, good. Good news. All right, submarine. So we, all right, so we got a submarine. And it's below the water, because it's a sub. All right, so it's 250 meters below the surface. So if you measure straight down to your sub, which is clearly that's a sub, 250 meters straight down. But your sub's going to start approaching the water level. Totally. Going to go like that. And it's going to ascend at an angle of 22 degrees from vertical. So the angle measured off of the vertical. My friends who just came out of trig, you're going, oh man, this feels like a bearings question. It is. It's like a baby bearings question. So this angle right here, this is 22 degrees off vertical. So instead of going straight up, the submarine is going 22 degrees east of north. Did you just get nightmares? You're like, no, don't talk about those. We're totally going to talk about those, by the way. You just ignored it. Oh, that's sad. All right, so how far will the submarine travel before it breaks the surface? So they want to know the distance that the sub traveled. They want to know this guy here. So if I look at my triangle, which is very poorly drawn, I have the hypotenuse and I have the adjacent leg. So which trig function should we be using here? Cosine. So you have cosine. This time we know the angle is 22. And it equals the adjacent leg, whoops, over the hypotenuse. And some of you already know exactly what to type in your calculator. And if you're not sure, you're just going to solve it like a cross product proportion. So x times cosine 22 equals 250, and then in order to solve for x, you're going to divide by the cosine of 22. So just so we're clear, on your homework, on your tests, everything that you're showing to me for evidence, I want to make sure that something is written down besides just answers, because I'll be giving you the answers, and I need to see some work on your end, guys. So I realize not all of you are going to show every single algebraic step. I get that. Some of you are just going to type it in the calculator. Then I need to see what you typed in your calculator. So you need to write that part down. Got it? What'd you get, by the way? 269.6? All right. Meters. Good labeling. Labeling is going to become uber important to us in the next part of our lesson. Oh, the ladder leaning against a building question. Everybody's favorite. All right, so this is a two-part question. They want to know, well, they have a lot labeled for you already, so that's nice. Just make sure you understand that the 70.1 degrees is this angle down here, which is referred to as the angle of elevation. They want to know two things. The first part is how high up the side of the house does the ladder reach? So let's call that Y. And then the next part of the question says, what's the horizontal distance from the bottom of the building to the bottom of the ladder? So they want to know this part. I'll call it X. So since we have two parts of the question, let's set up two different trig. Well, we'll come back to the two trig proportion option in a minute. Let's find Y first. So we have the hypotenuse, and then if we're trying to find this Y over here, that is opposite of our angle. So we have opposite and hypotenuse, so we should be using the sine ratio. So sine of 70.1 equals opposite, don't know it, over hypotenuse. And this is a nice easy proportion. You're just going to cross product, multiply by 30. And I got 28.2. Can I get a confirmation on that in feet? Okay, cool. So this length right here is 28.2. You have options for how you're going to find the next answer. We could just go ahead and set up another trig proportion. If you're going to find x, you're probably going to set up cosine would be my guess. Anyone have another way? You could just do Pythagorean theorem, yeah. Now we do run into a bit of an issue with truncation. We chose to round to the 10th place. Frankly, this problem is not really important to me, so I don't care if we've truncated a little bit, but if it's like my job and I was trying to make sure someone didn't, like, you know, blow up in a rocket or something, then I might keep more than a 10th place decimal, you know? But, you know, it's a ladder leaning against a house, so who cares? So either way, you get approximately 10.2 feet. Could be off by a 10th, depending on rounding and truncation. Alrighty. This is more our speed, and thank goodness they drew this picture for me. However, I do think there's something in your homework where it's kind of like this, where there's a baby and a mama triangle, and you got to draw it yourself, so try. We have this tower, which is, the goal is they want to figure out how big the tower is from here to here. The problem with that is it's not a part of a right triangle. So if we ignore our knowledge of law of sines and cosines right now, the way we have to solve this triangle is by using mama triangle, baby triangle. So the big triangle, this guy, and his angle down here in the corner for the big triangle, 58 degrees. So if we use this adjacent leg, we could find, and I'm kind of running out of room here, but I could find this entire height. I'm going to call it A. So I'm going to set up, let's see, adjacent and opposite would be tangent. So I'm going to set up the tangent of 58 degrees equals, I don't know, over 100 feet. And then, got a little baby triangle there, where I'm going to use his height, I'm going to call it B, and we're going to set up a very similar trig proportion. Tangent of, this time the angle is 30 degrees, is B over 100. So they're solved very similarly, except the problem is I don't want either A nor do I want B. What do I want? I want the difference of A and B. So if you took A and subtracted B. So after a little calculation, let's see, I got A to be 160.0. What do we label in here? Feet. And then I got B to be 57.7 feet. So then the tower is 160 minus 57.7, which is 102.3 feet. Any of my trig friends having fond memories of law of sines? No? Have no fond memories of law of sines. Okay. Well, it's coming back later. Don't worry. We'll get to you. All right. Moving along. Find worksheet. So now you're totally capable of finishing the bookwork from yesterday. I told you guys kind of hang out and not do the application parts unless you wanted to try. And a lot of the application questions, they look like they're multi-part questions, like there's part A, B, and C. But part A is like draw a diagram, and part B is set up the trig. So it's stuff you would have done anyways. It's not like extra stuff. Can you find worksheet 5? Please. The good news is worksheet 5, like the whole front, almost the whole front, I should say, is stuff we've kind of already covered. So, with the exception being the degrees, minutes, seconds stuff at the beginning. So my friends who just got out of trig, at the beginning when you guys were talking about like how to measure angles, you discovered, well, this is some vocab. So let's start here. The initial side is going to be on the positive x-axis, and then angles open counterclockwise to be considered positive. This is kind of leading you guys in towards the unit circle. That's our next event. Oh, speaking of the unit circle, the formula sheet you guys have, the unit circle is obviously on one side. You do have a unit circle test coming up on Friday. That's the only summative you have this week, is just the unit circle. And it's just like you've always seen the unit circle test, which means it's timed. You don't have a lot of time. You got to get it right, which means you got to memorize it or how to develop it. And it happens Friday. So tomorrow will be the first time that we officially develop a unit circle together, and then we'll do it again on Thursday, and we'll probably do it again on Friday before you take your test too. So in the back of your mind, start studying that as well. I know some of you have not fond memories of the unit circle test from algebra, so it's It's okay. You'll get better at it. The terminal side is where your angle stops, and then the angle is measured in between, like we said, in a counterclockwise notation. If you're measuring clockwise, that means you're going to have a negative angle. We'll talk more about that tomorrow. So this is newish, depending on if you took trig. So you can convert degrees to degrees, minutes, and seconds. So just like how you can measure distance and make your increments smaller and smaller, you can do the same thing with degrees. And this is utilized, I think, in nautical measurement and also aeronautical measurement. I personally don't use this because I don't do either of those things. So, you know how you can take a mile and you can break it down into feet, and you can take a foot and you can break it down into inches? Well, same thing here with degrees. So you can take a whole degree, you could break it into minutes. There are 60 minutes in 1 degree. That sounds familiar, doesn't it? Yeah. Sounds like an hour to me. Think about your unit circle, guys. It's a circle. Our clock is a circle. These are not coincidences that are just happening. They're made that way. And then you can break down a minute into seconds. There's 60 seconds in a minute. So quick question, how many seconds are in a degree? 3,600, right? 60 and 60, just like how many seconds are in an hour. There's 3,600. Okay. So none of you do this. This is the old way of converting from a decimal to degrees, minutes, and seconds. All of you young people use your calculator. It took me like 4 minutes to figure out how to do this on the calculator because I never use it because I'm old. But all you young people told me, Abruzzo, there's a button. And I went, oh, I forgot. So what I need you to do is on your calculator in the home screen, please type this decimal. And then go to your angle menu. I already forgot what the decimal was. Well, whatever. Just type some decimal. I don't care what you type. And then you're going to go to the angle menu, which is second apps. And one of the options is to convert, that's what that arrow means, to degrees, minutes, seconds. So you're going to choose that one and then hit enter, and it's going to convert it to degrees, minutes, seconds for you. So the one that's on your paper is not that one. It's this one, 213.875. So when you go to your calculator, and we're not doing this business. Well, this one we actually will, but you're going to go to second apps, which is the angle menu. And you're going to choose the one that says to DMS. What does it tell you? Obviously it's 213 degrees. What's the minutes? 52 minutes. That's the symbol for minutes, by the way. And 30 seconds. Now, by the way, in that menu, you'll notice that there's a symbol for degrees and minutes, but there's no symbol for seconds. Someone from Trig, tell me where you can find the seconds key. It is on your keypad somewhere. Alpha plus. Yes, there's a little, looks like quotation. I'll be honest though, even Old Dinosaur, now that I know the calculator can do it, I will do that question with the calculator, but I'm not going to do the next question that way. Because I don't like to go find all the symbols. It annoys me. I think I'm too old to like have the patience to do it. So for me, when I do this secondary question that goes the opposite direction, I just type what it is. So 89 plus 56 minutes, which means 56 over 60, plus 7 seconds, which means 7 over 3,600. So I just type this in my calculator, and that's how I convert it back to a decimal. But if you wanted to do 89 and then find the degree symbol, and then 56, find the minute symbol, and then 7, and then find the second symbol, you go right ahead. I just personally think it's easier to just type the fractions with the addition signs between them. Anywho, what'd you get there? 89.9353? Okay, cool. So, up to you. That's just my personal opinion on, if I was taking a test and I was a lazy kid, which I am still a lazy kid apparently, I'm just going to do it the easiest way that I can think of. These are going to be on your summative. There's a little bit on your homework, like a question or two at the beginning of your book work for today. You'll be fine. All right. So we've kind of already discussed radian measure before today. It's a little elusive to you unless you have a deep setting of trig, like you took the whole trig course, as to what a radian truly is. Anyone want to know? So a radian is just a different unit of measure for angles. It's the basic explanation for it. The idea is if you have a sector, and both of these are measured as r, then the angle between here is considered 1 radian. Okay, if all of them are measured as the same value. So a radian, if you want to convert it to degrees, we have a conversion for that, right? Oh, looking at me like you don't want to do this. Someone tell me the conversions from yesterday. How do you convert from radians to degrees? Let's start there. Okay, so radians to degrees, you go 180 over pi, times 180 over pi. If you go degrees to radians, you go pi over 180. And it's a little dimensional analysis trick, essentially, is what you're doing. Okay, so we discussed that yesterday. I'm going to skip over that part. I don't feel like we need more examples of that. We talked about coterminal yesterday. We talked about how to consider all coterminal angles. And yesterday I said a little different notation than what your book says. This is what your book says. It says alpha plus 360n for degrees. Yesterday we just said something like degrees, and then we said plus and minus 360k. So your book does two things. It changes n for k. That's kind of synonymous in math. N meaning any integer. K also means any integer. And the reason they don't do plus and minus is because when they say it's an integer, integers can be negative on their own. So like adding 360 times -1 is really subtracting 360. So for me, I like this notation. It just helps me. Now for radian, a little different because a rotation in radian is not 360, it's 2 pi. So yesterday we said the conversion was radian, and then you can either add or subtract rotations of 2 pi k. So again, your book uses n, I use k, I use plus and minus, book doesn't, it doesn't matter, it's all the same thing. Alright, I'm going to skip all that business. You guys did fine on it yesterday, and you have plenty of practice in your homework. Did coterminal already. Alright, here's the new stuff. 5b, find it. On your formula sheet, there's a box at the top of one side of your formula sheet that starts talking to you about a whole bunch of formulas. This is where the formulas for arc length, linear velocity, angular velocity are all going to show up. And all my trig friends just went, oh no. Yes, the wheel is spinning questions, revolutions per minute, those guys. We love these questions, right? So I tried to teach this last hour with a numb mouth. That was fun. We didn't get very far. I'm going to do a better job here in third hour. All right, so first formula is the arc length formula. And it's pretty basic. The reason it's basic, though, is because we're assuming that you're measuring theta in radians. If you don't have theta measured in radians, you either have to use a more complicated formula, or frankly, you just convert to radians, which is just as simple. So that's why math people like to use radian measure, because it simplifies everything that follows up. So arc length is the measure of the distance around the circle. So it's a portion of your circumference, if you want to think of it that way. Arc length is important. I'm sure there's lots of applications for it, most of which that I come up with are really stupid, like the length of your pizza crust. Like, you don't care about that. But there you go. It's an arc length. But there's some new formulas coming up, or new to some of you at least. Linear speed and angular speed. So linear speed, also known as linear velocity, those are synonymous formulas for math. And then there's angular speed, also known as angular velocity. All right, so here comes a bunch of Greek letters for us. The next slide shows you what's on your paper, but it looks pretty similar to this. They give you linear velocity, whoops, wrong. Linear velocity as, and I don't know why, but it's using V, which a lot of kids think it's a V. The symbol is actually this. It's a fancier V. It's a Vans V, isn't it? So it's V equals S over T. All that's true. But didn't we just find out that S is really R times theta? So another way to say this formula is R times theta over T. And then there's going to be one more formula. I just want you to write it down for now. It's R times omega. Looks like a W, but it's a big fat weird bubbly W. We'll come back to this last one in a minute. This one and this one are both on your formula sheet, I believe. I hope. Okay. And I'll be honest, guys, this is the one we use the most. Put a big star next to r times omega. Linear velocity is radius, r is radius, times omega. Now, what's omega? What's this? It's angular velocity. So it's the radians that you travel per unit of time. Remember, theta is always radians? So here's what I want to point out to you. Do you notice that theta over t shows up right there in the formula? So they just substituted theta over t for omega. That's where this formula is coming from. So I'm sure you had to like derive 1,000 formulas in trig, and you don't want to think about those anymore. You might want to write yourself a little note somewhere in your notes. It's not always the case, but what I will tell you is, generally speaking, the first thing you're going to do in most of these application problems is you're probably going to find the angular velocity. And then the second thing you're probably going to do in these problems, not always, but often, is you're going to calculate the linear velocity by using r times omega. So it makes sense that you're going to find angular velocity first, and then you're going to use it in the next step. I'm not saying every single problem, guys. In fact, there's problems coming up next in our notes where we don't do this at all. We're just trying to convert, trying to get you used to the idea of converting between these variables and watching your labels, because I think our trig friends will warn you that labels is kind of where they kill you. I'm going to take, and I know every teacher takes a little different approach, I'm going to take pretty much a dimensional analysis approach. So what you do in chemistry is what we're going to do here as well. I just think it's more comfortable for kids to do it that way. All right, so some labels for linear velocity. It's going to be some sort of distance divided by time. So things you might see are feet per second, centimeters per minute, you know, things like that. So just make sure if you're supposed to be labeling a linear velocity question, you don't tell me something weird like radians per minute, because that's weird. Angular velocity, however, is measuring angle over time, but remember, it's always radians. So it's going to be a radian, a number of radians divided by time. So things like radians per minute, radians per second, and radians per hour. And I think that might be the trickiest thing, is sometimes a kid's doing a problem and they do all the calculations properly with one exception. It'll say something at the end of the question like, I want your answer in, you know, feet per minute. And they gave me an answer that's feet per second. So they didn't continue on with their calculations. And I will tell you that on my test, if I do that to you, where I have you convert like some other dimension that has nothing to do with the PreCalc, I probably put it in bold. Like bold. So it's sad when you don't see it because it's in bold. All right, let's try some examples here. This one's already done for you, and I'll be honest, the way the book kind of wrote it out, I kind of find it a little confusing. So, I don't know. If you like the way the book did it, it's fine. I'm just going to do it a little differently. So we're going to determine the angular speed and the linear speed, and we're literally going to do it in that order. So the first thing I'm going to do, woo, that's not what I wanted. Okay. The first thing I'm going to do is find the angular speed, which is that weird omega thing. And then the second thing I'm going to do is find the linear speed. The doors have opened. Alright, here we go. Step one, we're going to find, you don't have to write this down, you can just watch. It's done already on your paper. It's the same work, they just kind of, they grouped it together weird. So we're going to find the angular velocity, and we're going to start by using this clue. It says that there's 8.2 revolutions completed in 3 seconds. So if I think about angular velocity, I was just told that the label on angular velocity has to be like radians per time. So we have time, and I'm just going to kind of read through the question. It doesn't say anything weird like I want your answer in something per minute, so we don't need to convert seconds at all. but right now I have revolutions, not radians. So there's going to be some like synonymous math fraction that helps me convert between a revolution and radians. So I want to cancel out revolutions. How big is one revolution when you call it radians? 2 pi radians. Very good. So I think I'm there, guys. The revolutions are gone. I have radians per second, which is an appropriate label for angular velocity. I would like a decimal answer here. So if I typed 8.2 times 2 pi and divided it by 3, I got like 17.2 radians per second. If you left it in terms of pi, there's nothing wrong with that, and it's probably mathematically more appropriate since we're not done, but whatever. All right, so step 2. Now we're going to use that angular velocity, and we're going to find the linear velocity, because we're going to use the formula, which is r times omega. So somewhere in my problem, we were told a radius. Did you find it? The distance from the center of rotation is 7. That's the definition of a radius. So 7 centimeters times this angular velocity you just found comes out to approximately 120.2. So the label on linear velocity is distance over time. I didn't write down my label. That was naughty. What was the label on the radius? How far distance are we talking here? Or what is measured in, excuse me. Centimeters, very good. Per, what was the time? Seconds, very good. So whenever I finish these problems up, I just stop and I go, do my labels make sense? Because linear velocity is distance per time, so centimeters per second. All right. The book did a little, all the calculations are there in the same, they just kind of utilize the formulas a little differently. And I find almost everybody in here has either had chemistry or in chemistry, and you're very comfortable with dimensional analysis, so I feel like that's probably just a better approach. So. Or not. All right, so these are examples of, we're still going to use dimensional analysis, but these are not the typical questions where like you're going to find angular and linear velocity like we see in our textbook problems, and also the ones that you're going to see on your test. So this is just kind of playing around with dimensional analysis. So let's do one of them. I'm not going to do number 6. We currently have an angular velocity of 2.7 radians per second. And then I'm looking ahead, and they want revolutions per minute. They're not happy with my labels, apparently. So we're not actually calculating anything different. We're just converting. So I need to convert radians to revolutions, and I need to convert seconds to minutes. So let's start with how do we convert radians to revolutions. So we're going to use that same fraction that we used on the last problem, except we might need to flip it around depending on what we need to cancel out. So radians needs to go. So 2 pi, buckle your seatbelts. The plane's taking off. All right, 2 pi radians is going to cancel out the radians there, and that's the same size as 1 revolution. And then the other thing we need to think about converting is they want per minute. So this next fraction is going to help me knock out seconds. So there's 60 seconds in 1 minute. So these equivalent fractions that we're using, they can be flipped around depending on what you need to cancel out and what you need to keep, just like you do in chemistry. Okay. So this is my favorite part of these problems. I get to cancel things out. So the radians are gone, and the seconds are going to cancel, and I end up with revolutions per minute, which is exactly what they wanted. So I'm on a roll. Here we go. On your calculator, please. 2.7 times 60, and then you're going to divide it by 2 pi. Now make sure you use parentheses if you're doing this in one step. Even around the 2 pi. The door's shut. All right, so we got, what was it, 25.8? And then it's revolutions per minute. I totally accept an answer with a label of RPM because I know what that means. All right, did we get that? Were we able to all type that properly? Okay, cool. All right. Oh, we're doing well. Good, good, good. All right, this next one. This is kind of a weird question. They won't usually ask this too much. So they want us to find the radius, this is an atypical question, but it's kind of fun. I'll show you what you have to do. You have the linear speed, and you also have the rate of rotation. So we have linear velocity and angular velocity. kind of, except it's not measured quite right. So let's go back to the question itself. I want to find the radius. So if I think about all the formulas that I have, the one that kind of stands out to me is this guy. Linear velocity is radius times angular velocity. So if you rearrange that equation for me, if you're trying to solve for radius, that means you're going to take your linear velocity and you're going to divide it by your angular velocity. But we got problems, people. Because look at how they provided you those two clues. We do have linear velocity and angular velocity. Kind of. This is linear velocity. But what's wrong with your angular velocity? It's in revolutions per minute. And what was linear velocity given to you in? Meters, which who cares, per second. Yeah. All right, so we need to do some converting. Since this is the one that has the most problems in it, I'm going to convert that one to what I need. So we need to change this to radians per second. All right, here we go. 120 revolutions per minute. All right, I got two things to change, so that means I have two fractions. Here we go. How do you convert revolutions to radians? What's that fraction? 2 pi radians is 1 revolution, so just make sure they go in the right order. I want to get rid of the revolution. Knock it out. I want to keep 2 pi radians. All right, goal 1 accomplished. Now I need to change minutes to seconds. So in 1 minute, because I need them to knock out, there are 60 seconds. All right, favorite part. Everything cancels that needs to cancel. And we're going to have angular velocity given to us in radians per second. Good news. This is angular velocity. It's going to be in radians per second. All right, little calculation on your part, please. What's a decimal answer? 120 times 2 pi, and then you're going to divide it by 60. Whatever 4 pi is. What's 4 pi? One more time, what is it? 12.6, okay. So that's your angular velocity. And remember this formula from a year and a half ago? It said your radius is your linear velocity divided by your angular velocity. So radius is your linear velocity, 24.8 meters per second, divided by 12.6 radians per second. Now this is kind of a weird anomaly. In the math, kids get a little confused because they're like, what happened to the label of radians? It's not considered in this next answer because your answer is going to be the length of the radius, which is just the length. So I got approximately 2, but what does yours come out to depending on your truncation? 1.96. Okay, so 1.97 sounds wonderful. And then a label of, did you catch the label on the distance? It's somewhere in your problem, meters. Very good. Very nice. So that was a very strange question. That's not a typical question that you're going to see on your homework or your test. All right. Do we have time for this guy? Yeah, we do. All right, transportation question. So this one is a little hard to see on your paper, so the wonderful Mrs. Hoffbauer kind of redrew the arcs separately from each other. So the 14 feet is the distance between each lane. So all the way across both lanes is going to be a distance of 28 feet. When I first did this question, I was a little confused because I wasn't getting the right answer because I couldn't read, apparently. It said a lane is 14 feet wide, which makes a lot more sense because otherwise cars would hit each other. All right, right? It'd be bad. So they want to know how much larger the outside edge of the far lane is than the inside edge. So, okay. So they want the distance between, or the difference between these two arc lengths. So this guy, let's call it arc length 1. And then this guy, let's call it arc length 2. So the formula that we're going to be using is just a really boring arc length formula, which says r times theta. But we got a problem, people. While it is a simple formula, it only gets to be used if your theta, your angle, is measured in what? Radians. We don't have it in radians, but I think we could figure that out real quick. 180 degrees. You can either directly convert it if you want, or you can just tell me. Anyone know how many radians is 180 degrees? It's pi radians. All right, this is the theta that you're going to be using. So, finding our first arc length. It is the radius, 1,000, times theta, which is pi, and then arc length 2, oops, wrong color. Ari, you should be able to start the next bookwork. Get at least to number 29, okay? Arc length 2 is his radius times pi still. And then if you calculate these and you subtract them, the difference is what they want. So I got about 88 feet when you go ahead and throw the pi's in your calculator. All right, so we're going to kind of pause our lesson there. We should be going on to worksheet 6, but we're going to be out of time. So tomorrow we're going to continue on with worksheet 6, which is going to start talking to you about area of a sector, which is just another formula. I think on your bookwork, which is page 238, you should be able to get through a big chunk of it, like at least to number 29. And of course, you're maybe catching up on yesterday's work too. Tomorrow, I really want you guys to be able to concentrate on the unit circle studying, so try not to leave yourself with too much homework overlap in here.